Everyone, I'll try to talk about what this all means for realistic system in ERCOT. So as Jason briefly mentioned, we are not synchronously interconnected with the rest of the US. ERCOT covers about 90% of Texas electric load and 75% of Texas land. Our peak load is about 75 gigawatt, and we have a large number of generators, transmission lines. You can see it on the slide. We have 4 HVDC interconnectors. So again, just to stress out, we are not synchronously interconnected with the rest of the US, and we cannot rely on our neighbors for example, for frequency support. So everything that happens in Texas stays in Texas and has to be balanced within ERCOT system. So there are some more details on this slide. I will not talk about everything. What I wanted to point out is that, maybe I'll get a pointer, give me a second. Yes, so I wanted just to stop on this chart for a little bit to say we're still 50% gas-based nature. So our generation is natural gas primarily. We have 25% of wind generation. This is all in terms of installed capacity. We have a little bit of coal left. I'll talk about coal retirements later in the presentation. 5% of nuclear, and then the rest comes from solar storage and some other small generation. So this talks about inverter-based resources specifically, and kind of shows development of inverter-based resources in ERCOT. It is rapidly picking up. We are currently at about shy of 40 gigawatt of inverter-based resources, primarily wind. Now solar is picking up and battery is coming. So in dark color here, you can see megawatt of installed capacity that already been installed, and blue is for wind, yellow for solar, and this dark purple is for battery. And this includes commercial projects already, and also projects that are synchronized to ERCOT grid. What it means is that they are already there and online, but still going through some sort of testing. And so they're not fully commercial yet, but they are, from the impact to the grid perspective, they are already there. And these lighter colors, they show planned projects going forward. So yeah, as I mentioned, we're currently at about 40 gigawatt of wind, solar, and storage. And then yeah, that's what I also wanted to mention, that in the next couple of years, it's almost going to double. So we're still planning to install quite a bit of wind, solar storage. One more thing, sorry, coming back to the slide, I think it's interesting to mention in the beginning, Jason was talking about penetration level, and so percentage of load that is being supplied by inverter-based resources. So we recently hit our new record, and we supplied almost 66.5% of load with wind generation at the time. Why I'm saying wind generation is because it's happened at night, so there was no solar at the time. This usually happens during shoulder seasons at night when load is lower and wind production is high. So Nick was talking about weak grid conditions. We have this area of in Texas Panhandle where we have, by the end of December last year, we had about 4.2 gigawatt of operational wind, and then a little bit more wind is planned to be added there. And then this other area, this marked in yellow, between this red and yellow, where even more wind generation is installed, so 2.8 gigawatt operational and 2.1 gigawatt planned. So in this upper area, there is very little local load, and there is no synchronous generation, or even if there are a few small synchronous generators there, they're usually offline when we have high wind conditions. So basically this area is all inverter-based resources only, And this is classical example of weak grid conditions. Why this area became popular for inverter-based resources development is because we limited transmission from this area for a while, and so resources on the left-hand side of this constraint were constrained and curtailed. And so people started building right outside of this area. And initially we thought it will deteriorate the system, but it actually helps because electrically it reduces electrical distance to the rest of the grid where major loads are situated in these big cities here. So that being said, we still have stability challenges in this area, as I mentioned, primarily associated with weak grid conditions. So we determined that short circuit ratio, what Nick was talking about, we determined what the limit is based on detailed offline studies that I'll talk about in the next slide. And we monitored this limit in real time until very recently, and I'll explain a bit more about this later. Then there is also voltage stability issue in this area. I think Nick also talked about it. If you have generation resources very far away from load and a lot of power needs to be pushed long distance, then keeping voltage at the sending end, receiving end, and along those long transmission line becomes a challenge. And so that's what causes additional transmission limits, export limits in this area. And so transmission lines that we have there, they cannot be loaded to their full thermal capability because of these concerns. And then there are dynamic stability limits. So these are caused by disturbances like generator outages and faults. In the right-hand corner, you can see just this was one of the classical examples of voltage stability issue due to weak grid conditions, and that was measured in 2012 during an event that happened. So you can see that voltage is not staying constant or nearly constant, but is oscillating, and the oscillations are becoming higher and higher. And this can be corrected, as Nick mentioned, by tuning controls of inverter-based resources and also coordinating controls of adjacent inverter-based resources in the area. Right. So as we saw this weak grid issues becoming a problem in Texas Panhandle, in 2016, we started doing detailed this electromagnetic transient studies. So these are studies done in different software that you would regularly do your system studies, and this requires a lot of modeling and modeling details that normally are not represented in regular studies. So that's the kind of special kind of studies that we need to do now. So that helped us to determine this 1.5 short circuit ratio condition to which we wanted to keep. So we in real time would monitor system conditions and limit generation in Texas Panhandle so that short circuit ratio in this area is not below 1.5, so that inverter controls remain stable. This issue is very complex. That number is not a magic number, as Nick mentioned. It's a complex issue. It needs to be studied. Different system conditions. You can actually go even lower. And also system conditions and topology are changing over time. So this limit always needs to be checked with additional studies. And so one of the examples of actually positive thing that just recently happened, the city of Lubbock joined ERCOT. So originally they were an SPP, and now they joined ERCOT, and this way they brought additional load and also 2 small generators into this nearby Panhandle area. And that provided sufficient system strength and support for time being, together with 2 synchronous condensers that were recently installed in Panhandle as well. And so once that area connected into ERCOT, we were able to remove this short circuit ratio constraint for now. And we're not monitoring it anymore in real time. So I mentioned synchronous condensers. Overall, synchronous generators They use power system stabilizers to provide damping to power system oscillations. And under high renewable conditions with limited or no synchronous generation in West Texas, we see in studies that it may lead to insufficient damping support needed to maintain stability during and after some disturbances. This is because when we have high inverter-based resource production, then some of the synchronous generators are turning off. And so what happens, we'll have this large bubbles that Nick was showing spread across the system, and they're just few. And so if you trip one, if you cut one wire and then they start oscillating against each other, and because you only have a few of them, these oscillations are maybe increasing in amplitude, or maybe it takes a long time to damp out. What happened as well as we added 2 synchronous condensers in Texas Panhandle. Let me go back just for a second. So we added 2 synchronous condensers in this area. As I mentioned, there is no synchronous generation in this area, and the rest of like large synchronous generators are on this side of the system and long transmission lines in between. So as we installed the synchronous condensers, they didn't have this power system stabilizers on, so like they were not designed to have those stabilizers. And in the studies, we observed that the cause of these oscillations are synchronous condensers because they don't have a stabilizer. So we solved one problem by installing synchronous condensers and increasing system strengths in the area. But on the other hand, there was another problem that we haven't anticipated that synchronous condensers brought about. And I think it's kind of in personal opinion, I think it talks about that maybe solution to issues on the grid that are to parts caused by inverter-based resources and maybe better solved by inverter-based resources themselves than rather than adding additional equipment. So this slide talks about increasing number of so-called generic transmission constraints that we have on the grid. So this basically much of the growth of inverter-based resources are concentrated in the West Texas Panhandle, west part of Texas, and then in the South. And they are contributing to stability constraints because they are far away from big loads and the rest of the grid where synchronous generators are. These constraints are not thermal, as I mentioned, they are stability related, and so we need to constrain flows on these transmission lines, sometimes way above or way below thermal rating of transmission lines. So we introduced these generic transmission constraints. These are constraints on corridors of transmission elements, and we need to monitor this transmission constraints in real time. Also, what complicates things is that limits on these transmission constraints, they change with system conditions. So depending on system topology, on inverter-based resources that are online at the time on day generation, the limit on a transmission constraint may change. So that just kind of complicates things, and we need to add to our tools real-time tools to identify those constraints and manage them accordingly. So as one example, we have these constraints in our security constraint economic dispatch. So when we dispatch generation in ERCOT area, these constraints are taken into account. And you can see we have this number of constraints increasing as we increase amount of inverter-based resources in our system. So what?
This is Debbie. You're about half time, just so you know.
Okay, that's great. I think I'm about halfway through. So what it causes that this transmission constraints, because you have inverter-based resources on one side of these constraints, and what constraints effectively are doing are curtailing wind and solar generation because it cannot be transferred. You can see that here installed capacity in every year for wind and solar, including synchronized capacity, and percentage of curtailment every year. And you can see this is steadily growing because of transmission constraints. And when you see here that it's declining, it means that something was maybe added to the system that helped to increase transmission constraint. But then over time, as more and more inverter-based resources are being added, transmission constraints start binding again, or there are new transmission constraints, and so curtailment still kind of steadily goes up. Also, one thing I wanted to mention is kind of hard to say here how much curtailment is because of over generation on the system, because there are times sometimes when we have enough wind and solar generation to and other synchronous generation online to feed more than what our system load is at the time. So that's called over generation. And sometimes these curtailments are just purely because of transmission constraints. And so if you look at what's purely over generation, these curtailments are, because of that, are much less than what caused by transmission constraints. But there are also times when a network is constrained, but we are still in over generation conditions. So in those instances, it's hard to say what's the main cause of curtailment. We overall, maybe, I mean, in other areas, you can see this renewable integration studies where people try to find limit of how much inverter-based resources can be installed on the system. And overall, we don't do this kind of studies. We do a range of planning studies that kind of capture all challenges that we might have on the system with all resources planned. We have several stages of those studies. But here's one where we kind of explored, and we just had this 70% penetration of inverter-based resources in the case, and that was just arbitrary case we picked from one of our planning cases. And we had, as a result, there was less synchronous generation online. We encountered wide area weak grid issues. We saw significant active and reactive losses across the grid. And so basically to solve this case in traditional power system simulation software that we normally use, we had to add a large number of synchronous condensers. It doesn't mean that we have to install and that's the only solution that's there. It just, we kind of wanted to see what it takes for a system to still remain stable in different disturbance conditions. So we added those synchronous condensers, and then we were able to solve the case, and the system was able to maintain synchronism and stay reliable for a number of disturbances and disturbance conditions. But what we found in the study that inverter-based resource control, traditional ones, they require sufficient system strength to operate stably. I think Nick talked a lot about that. We need to tune inverter controls in weak grid areas and coordinate between adjacent inverter-based resources. Probably grid forming inverters in those weak grid areas would help. That was kind of just a recommendation for something to explore further. And as I mentioned, even in this study, synchronous condensers were found to be contributors to instabilities. And I talked about that in the example previously, in realistic example with 2 synchronous condensers in Texas Panhandle. So we see similar oscillations even in this study where we add more synchronous condensers. So that's, I guess, not the only solution that's there and requires additional measures for system stability. So as I started talking about grid forming inverters, this is kind of my favorite slide to highlight a circular problem that exists. So as you probably gathered by now in my presentation, we are a system operator experiencing additional system needs with more and more inverter-based resources on the grid. But the challenge is, and we think that that would be optimal if these needs were provided by inverter-based resources, but we cannot go out and require certain capabilities and products if they are not commercially available. So what we do, as I mentioned before, we apply operational constraints. So we have this generic transmission constraint that leads to curtailments, and so it becomes difficult or economically unattractive for additional inverter-based resources to connect in those areas because they are now behind constraint and are restricted. Because there is more, or there's less inverter-based resources being built, then it's shrinking market for equipment manufacturers. And on the other hand, equipment manufacturers can actually do a lot and provide this grid forming capabilities. There are pilot projects out there that are already, been tested, but manufacturers don't have clear understanding of what requirements are, what are specifications, what is that we actually need, what do we require, how are we going to test it. And so there is this vicious circle that needs to open and get resolved, and I think this is where kind of policy changes and drivers are required, and maybe introduction of new market products that would provide incentive for this grid forming capability, where inverters could help to resolve these issues that they kind of bring about right now. So switching gears, talking about inertia a little bit. For us, as I mentioned, we're electrical island almost. We have only HVDC interconnection, and it's relatively small, so we cannot rely on that for frequency support and for inertial support. In the past years, we've seen quite a bit of retirements of coal generation. So here in the bottom part of the chart, you can see all retirements, and gray, that's coal generation. So you can see majority of generation that retired was coal and older gas steam generation. And then in the upper part of this chart, you can see additions of generation from 2013 all through 2020. And earlier on in this period, we had quite a few additions of gas-fired generation, combined cycle, and a few combustion turbines. And you can see that these additions, they bring about quite a big amount of inertia, because combined cycle replacing coal unit of the same size actually can increase inertia 1.5 times. So combined cycle unit of same size as coal has high inertia. That's what I meant to say. And so as a result, if you look at this 7-year period, we actually had a net addition of inertia of 14 gigawatt seconds. So it's a sizable chunk of inertia that we actually added to the system, even though we had retirements. But this is only in terms of installed capacity, in terms of what we have. It's not necessarily that at all times these generators are online and providing this inertia. And here I just wanted to bring up this same chart as before, showing inverter-based resources that were added to the system. And you can see that in the same period between 2013 and 2020, we added about 18 gigawatt of inverter-based resources that are effectively displacing synchronous generation and should affect inertia in the downwards direction. But what we observed, kind of surprisingly to us, even that between 2013 and 2020, observed average and minimum inertia was relatively constant. And this is because there are other factors contributing to inertia. We have our nuclear units, they are almost always online unless they are on maintenance. We have synchronous generators providing some ancillary services, so that brings them online as well. We have a large number of industrial generators on sites, on industrial sites. And these generators, they don't operate economically. They are there for industrial processes. And so they bring about, maybe they don't generate power into ERCOT, but they bring about a large chunk of inertia as well. What happened in March this year, though, is we hit 109 gigawatt seconds of inertia, and that's quite a bit lower than prior 128 gigawatt seconds of inertia minimum that we had before. And so this is kind of surprising. We suspect it maybe has to do with large number of plants on maintenance because of the maybe something to do with February freeze event. We want to kind of watch it closer and see if this trend continues. We determined that our critical inertia level is 100 gigawatt seconds. So we, at this time, with all frequency control measures that we have in place, wouldn't like to go below this level. And so we monitor inertia in real time. And if it starts getting close to 100 gigawatt seconds, operators have measures in place to address this and bring additional synchronous generators online. We have frequency containment reserves, so that what Jason was talking about, we have reserves to arrest frequency decline in case of a large generator trip, and we determine amounts of this reserve that we need based on expected inertia conditions. So if inertia is lower, we need more of this reserve. If inertia is higher, we need less. We recently introduced fast frequency response product, that also what Jason was talking about, so that effectively makes the frequency control faster, and that allows us to go down in required inertia online. So we can go from 100 gigawatt seconds to 90 gigawatt seconds once this fast frequency response product is fully subscribed by providers. So right now they're still just starting and going through qualifications. What was so currently, yeah, as I mentioned, sorry about that, kind of lost track. Currently, nuclear generation and generation that is providing ancillary services, they bring about sufficient inertia, but we keep monitoring that trend, and we'll see if it decreases as we go further. We also anticipate, as more inverter-based resources are seeking qualification for provision of ancillary services, as Jason mentioned, they can provide frequency response and fast frequency response as well, then they may displace synchronous generators that are providing ancillary services, and therefore inertia may theoretically go down. But as I mentioned, so far, we are not seeing this trend.
To wrap up in a couple minutes.
All right, I'll go quickly. I'll just see what I have. So this one this one discusses our interconnection studies. So overall, interconnection studies with inverter-based resources are becoming kind of more complex and sophisticated. We need to do a number of studies, as you can see here. Previously, we've been doing this portion of studies even for conventional resources. Now we're also doing this quarterly stability assessment because, as Nick mentioned, we also recognize that we need to look at each inverter-based resources not separately, but together, and what's the common effect on the grid. So we kind of group resources that are about to come online within the next 3 to 6 months, and we include them all into this quarterly stability assessment to see how they all affect grid stability together. And so this is very helpful and allows us to address them in kind of batch processing manner. And so, yeah, this is just to say typical timeline for IBR interconnection is 24 months. That's also kind of change from what we used to have before, where thermal plant development would take from 3 to 5 years. So this is much shorter time frame. So we're seeing changes to our generation mix that are much quicker than before. This is just to briefly talk about model complexity. So we initially struggled with model quality, and we needed to do a lot of work with quality of models that developers are providing to us. And now we have a process in place where during interconnection process, we go through several stages of collecting models, testing models, and now also developers are doing their own model validation. So before they even bring models to us, they have to prove to us that model is performing as expected and in accordance with our interconnection requirements. And then we also do in-house verification. So that helps us to have more fidelity in models that we have and in the study results that we get. I also mentioned this electromagnetic transient studies, these more complicated detailed studies that we're doing. We're now requiring all inverter-based resources to provide us models that would enable us to do these detailed studies as well. So just to summarize, we're seeing increasing stability and system strength challenges with more inverter-based resources online. I talked about complexities and time-consuming nature of studies that we need to do. now with more inverter-based resources and weak grid issues. Stability challenges that we had previously. We need for tighter voltage control and also maybe coordination across parts of the grid so that voltage control resources and reactive power resources can be optimized. We need to identify and manage stability constraints closer in real time. One of the things I haven't mentioned, we are currently in the process of implementing dynamic assessment tools in real time, so that this will allow us to do studies in real time and calculate generic transmission limits closer to real time. That allows more flexibility. We need to communicate early and coordinate with inverter-based resource developers, again, to make sure that we have good models and fidelity in our simulation results. And we're exploring ways to operate under weaker grid conditions by tuning controls in adjacent inverter-based resources and also adding certain things to increase system strengths. I also wanted to point out that we believe that weak grid issue is kind of more pressing, and inertia is maybe less of a pressing issue, as we see inertia not declining in proportion to additional inverter-based resources. And also new fast frequency response products are helping us to reduce critical inertia amount. So, I mean, it is declining. It probably become an issue at some point, but weak grid issue right now is more of a pressing issue for us. And with that, here are a lot of references, and you can go and read all of that. And I'm open to questions.
Thanks so much, Julia. That was fantastic, and a really good follow-up to what Nick and just presented. So there's a couple questions. I think we have time for one. Dan's more Texas specific, so maybe I'll ask David's, which is a little more general. Do the synchronous condensers that you showed, do they have flywheels to increase inertia to aid stability?
No, so they were added primarily to increase system strengths in the area and provide voltage support. So they were not designed to increase inertia, don't have flywheel. Okay.
And Nick and Jason, I don't know if you wanted to add to that and your experience of synchronous condensers with flywheels.
Yeah, I could just chime in. Right, you know, applying synchronous condensers dictates that you actually give a lot of thought to what it is that you're trying to fix, because they're effective solutions for a whole bunch of different problems, and you end up with different designs. But your question was right on, and you know, the condensers like the ones that Texas put in are actually relatively low inertia things. They're only, you know, inertia constant of about 1.
It's about 1.5, yeah.
There are 4 new, quite large, like 250 MVA class synchronous condensers that have been commissioned in South Australia recently. Two different OEMs that have flywheels, and they have inertia constants in the neighborhood of 8. So that is a technology that's getting some legs. Having said that, you know, you got to be careful, because inertia, as you heard from me repeatedly, is a two-edged sword. So, they can introduce those higher inertia machines can do good things for you, but they can also introduce some new stability worries. That's it.
All right, thanks.